Hello, everybody. Welcome to this new webinar from Sisgeo. So I'm very happy to see that you are many subscribed people and that your interest has been raised to the top for this new topic. Just technical things you will see on the GoToWebinar interface on the upper right corner. Question mark, so a box with a question mark, and this is the space where you have to address your question. So during the presentation, you will have some question arising, and I invite you to write them in this corner, in this option, and then we will take some time at the end of the presentation in order to study and to reply to the most interesting questions. Then I would introduce this topic talking about water. So water, as you know, is everywhere at the surface of the globe, in the ocean, and also in the underground of the continents. So water is a resource that has to be managed. So to manage water, we have to focus on the quantity of water, the movement of water, and also the risks that are linked to human activities. So the risks are mainly in geotechnics and construction sector is mitigated through monitoring. So the monitoring is an activity that aims to provide data in order to monitor and then to take the right decision. So how to monitor water in the ground? So the answer is piezometers, obviously. So let's focus a bit on this system. So we will see in some different chapters the piezometers, but just previously, just in a small introduction about Sisgeo, if you don't know us, then we will handle some definitions in order to speak the same language and to have the same terms, the same vocabulary. Then we will focus on our specific systems, and in the third part, some specific applications that are linked to special device piezometer sensors. So we have plenty of different piezometers. You will see that there are some applications for each of that. And last, question and answer, as promised. So first part, so such an introduction, let's say. So the group Sisgeo. Sisgeo, who we are a designer and manufacturer of geotechnical and structural monitoring instrumentation. So we are global leaders, so we are providing all the world. And I used to say that we are more than a supplier because in our group, we have plenty of specialists coming from different areas from the globe and also from different sectors. We have geophysicists, we have geotechnicians, we have mechanicians, etc. So we can provide help for many of the main applications that we cover, like dams, tunnels, excavation mines, etc. So based in Italy, we have been acquired by Eddify Technologies Group, section remote monitoring, which is based in Canada, very recently in June this year. So within this new group, we are now collaborating with Sensive Sensor Networks, so Sensive based in UK, Sensor Networks based in the United States, and Sisgeo Hugenberger, which are the entities that you, I think, previously knew. So Sisgeo is divided into many subsidiaries located in Italy, France, Germany, Colombia, and Hugenberger, which is also part from the group, Sisgeo previously and now Eddify, based in Switzerland. About myself, so I'm engineer, geologist, geotechnician. I started my journey in this area, in this application in 2004. Now I'm a sales engineer at Sisgeo since 2015, so 10 years now already. Time goes by. And I've become a kind of expert for geotechnical instrumentation, and I'm teaching in some engineer schools as well. So after this small introduction about us, let's see the main topic that we have promised to you. So what is a piezometer? Etymologically, it comes from the ancient Greek, to divide it into two, piezein and metro. Piezein means to press and metro to measure. So it's a measuring instrument used to quantify the pressure exerted by the fluid at a given point in the underground. So then you will need two physical quantities in order to quantify it. So the free height of fluid, this is the piezometric level expressed in meter, so it's a length, or the flood pressure expressed in the pressure unit, so Pascal, for example. So what is the purpose of a piezometer? So in construction world, so the general application are water table monitoring, pore pressure, or the migration of water and the possible pollutant inside it. Also, with the pressure transducer, pressure sensors, we can also measure atmospheric pressure and the pressure contained inside a circuit. About the piezometer, this activity and this monitoring is covered by a standard, ISO standard, which is 18674-4, and this standard explains exactly how to use a piezometer, the main principles, and how to monitor well and use well your devices. Mainly, we can divide the piezometer into two types: open piezometer and closed piezometer. So what is the difference? So the difference lays in the contact between the water contained inside the system and the atmosphere. In the open piezometer type, so the water contained inside the system is in direct contact with the atmosphere anytime. So a column allows the access to the clean water, so the water exempted from any soil particle. So the advantage of this is that you can take some samples in order to make some analysis afterwards. In order to measure these types of piezometer, you will use two main devices possible: water level indicator or a pressure sensor. In the closed type, on the contrary, the water is not in contact with the atmosphere, it's sealed. So it's a small system using a filter, a low volume chamber, and very important, an elastic diaphragm. I will speak about it a bit later. So we measure basically the deflection of this diaphragm, and we use a technology that detects with micro deformation the deflection of this diaphragm. For this, the main application is the pore water pressure monitoring. We can also use this kind of closed system to monitor circuit pressure. It's the same principle. So what is pore pressure? So pore pressure is acting in low permeability soils. So this is the pressure of the groundwater held within soil pores. So in this kind of soils, the water flow is very slow. So it's affecting the pressure dissipation. So whenever you are loading the ground, the soil, or performing an excavation, then you can get excess pore pressure because it cannot dissipate because the water flow is very slow. So monitoring the pore pressure is very critical for safe geotechnical engineering. So the main principle resumed, summed up, for the tubes and the open piezometer, so you have a protected water column, which is defined with a borehole and a casing inside it. So this casing, at some parts of it, is permeable to water, and the zone around the plain casing has to be filled depending on the application. For the closed piezometer, so the closed piezometer is defined by a very small volume of monitored soil. So the smaller, the better. And the zone around the system has to be watertight according to the geology. So you cannot apply this kind of system for any type of geology with the same system. You have to adapt your system to the situation. So about our solutions, so we basically produce casings and filters, water level indicators, and pressure sensors. So the casing and filters filter the soil to have only water inside. The water level indicator detects the water depth, and the pressure sensor, they measure the pressure and the pressure changes. That was it for the definition. So now we can enter into the range of systems that we provide in Sisgeo and we produce. About open tubes, we are talking here about piezometer casing. So you will have a PVC column of tubes which are screwed together. So on the principle, we provide 3 meters long tubes. You can sometimes find shorter tubes, but basically it's 3 meters. And some tubes are plain and some tubes are filtered. So they are screened or they are slotted, like on the image here. You can find slots. And also you can find porous filter. So this column allows to build a clean water column inside the underground. So inside the tube, the water will flow without any soil particle in order to measure the water level inside. So the different diameter that we provide are here stated at the bottom. So they are expressed in inches. So these standpipes, tube piezometers, their aim is to monitor the water level in the permeable soils. So this column, which is screwed together and inserted into the soil, has to be backfilled with pebbles or sand in order to allow the free water flow. If you make a seal, then you won't have any water coming in. So you have to respect the permeability of the soil, surrounding soil. If you are in the steady state, then you monitor, you measure the water level. If you are in the frame of a pumping test, for example, then the water level that you will measure is used to measure and to calculate the permeability of the ground. So I drive you to the ISO norm referring this pumping test, so you will see how to use the piezometer inside these pumping tests. These tubes are measured with water level indicator or piezometer sensor, and this piezometer sensor can be also equipped with a data logger in order to retrieve and to register all the values. The same tubes, the same tube that you have seen before, can be used also in a different way. So it's what we call Casagrande tube. They monitor the pore pressure in low permeable soil. So on the contrary of the previous, you use the same column of tube, but you will seal the filter with means of a bentonite seal. So bentonite is a clay which is swelling and makes a seal, a sealing. So the filter is laid into a sandy level. Then you build a bentonite plug, which has to be quite dense and quite let's say in volume, I would say 1 meter is the minimum. And then you have the plain column of PVC tubes that can be single or double. Here, single on the left and double on the right. What we measure inside it, so when the water is stabilizing, this is not really the water table. This is piezometric, the pore water pressure, which is raising in the form of a piezometric line. So this can also be measured with a manual water level indicator or with a piezometer sensor with means of the data logger. Then about the filters, we provide 2 types of filter, so the single one or the double one. So these 2 filters have the same porosity, 14 microns, made in polyethylene. The length is 200 millimeters, so it's quite short on purpose because the volume has to be small. And the column, when it's single, you will find inside it a conical port. So this conical port, we will talk about it at the last slides. It's made for welcoming a piezometer sensor, special piezometer sensor. Or the double column can be used in order to flush. So when you are using a piezometer for very long-term operation, then the risk is that the small fines of clay can still enter inside the filter. Also, you can find bacterial colloids. So this will affect the permeability of the filter and then affect the performance of the monitoring. So in order to avoid that on the long term, you can flush, so inject water in the one pipe and then to let it flow from the other one. Then you let stabilize again in order to measure your real water table. About measuring the open tubes, so we saw we have the water level indicator, sorry. So the water level indicator is a very small and very easy device, simple device. So it's a stainless steel band with a graduation in millimeter on it, coated with nylon. And on the side, there are electrical conductors. So the principle is that you have an open circuit. So the circuit is made from the battery here. So the battery is linked with a buzzer and a light. Sometimes you can find also a display on this model in order to display the temperature, because we can also have a temperature sensor inside. And whenever the electrode contained in the tip touches water, then it closes the circuit, because the water contains some ionic elements that closes electrically the circuit. So when it touches the water, then it activates the buzzer and the light. Then from this moment, you have to read the depth on the graduation according to your reference at the surface. So what we produce in Sisgeo here, you can see the lengths that we can produce: 30, 50, 100, 150, 200, 300 meters. Now, let's speak about sensors. So the sensor technology has main principles that are always the same. So first, the anatomy of a piezometer sensor is made into three main parts. So one is the output cable. Two is the end tip that can have various forms, as we can see further. And last, the main body. So the main body contains very important features inside, so parts. So first, the end tip is closing the system between the environment and the main body. Inside this chamber, you just have water. So at the beginning, when you get your supply, it's air, but you have to fill with water. From this chamber, it's separated from the main body electrical part with a diaphragm. So this diaphragm is a very important piece that will have a deformation. So whenever the water presses on, exerts a pressure on this diaphragm, then this diaphragm will have a deformation. So then you have the sensing zone measuring this deformation. The sensing zone is connected to the cable, the output cable, with some signal conductors. And very important, you have this sealed zone. So we use in Sisgeo epoxy resin that allows the electrical circuit to be immersed into water, sometimes 500 meters, sometimes less. So we have to take care a lot of this part, sealed zone. So remember this picture. I will remind it for further explanation for a special case. We have two main technologies in Sisgeo. We produce strain gauge piezometer sensors and vibrating wire piezometer sensors. So what is the difference between strain gauge and vibrating wire? So strain gauge uses the piezoelectric effect of gauges. What does it mean? So piezo, remember, etymologically means to press. So you use some copper foils, and these copper foils, their resistance change whenever you press on it, and whenever there is a force applied on it. So applying this principle on the diaphragm, so the diaphragm is basically a sort of coin and made in ceramic here. So this coin has a circuit of copper print on it, and then with means of a Weston bridge circuit, we can average the deformation on the surface, because you have strain and compression at the same time here. Then the output, or the signal that comes out, can be directly the Western bridge in millivolt per volt, but with it, you are limited to a certain length of cable because the signal is very small. Or we use also a transmitter, a converter, in order to enhance the signal up to 1 kilometer, even more. And this signal is made in 420 milliamps. The main advantages of this technology is that you can run long cables with the transmitter, obviously. This is very accurate, precise, and stable. Also, the particularity is that the strain gauge piezometer sensor is quite quick and reactive, so you can use them for dynamic monitoring and effects. And the signal is very simple, so you can measure with plenty of industrial devices this kind of signal. So it's just an electric value that you can convert into the physical unit. Now, but about vibrating wire piezometer sensor. So the principle, I'm sure many of you know already this principle, but I will just sum up. So this is a wire which is in tension between 2 points, and this wire is excited with means of the electromagnetic coil. So the resonance creates an output signal. In order to translate with easy words, this is the same as a violin string or a guitar string. So when the guitar string is extended in tension, and when you are pinching it or exciting it, then you get a sound. So the analysis then is a very complicated signal. So it's a vibrating signal. You have to analyze it with a Fourier transform in order to process and filter the noise. What is proportional to the pressure is not the frequency, but the frequency squared. So this is why when you get a sensor, you don't have the measurement directly in frequency. Basically, for the calibration sheets, you will see we express it in digits. So digits are basically squared frequency. So the main advantages of this technology are: first, there is an embedded surge protection. Second, it can run very, very, very long cables. We can measure negative pressure with it because the wire can be more stretched or less stretched. Then we can deduct some negative pressure from it. Also, I jump over. You have an NTC temperature, so temperature sensor. Anytime whenever you have a vibrating wire sensor in Sisgeo, you have also an associated temperature sensor. Important to note that this kind of technology does not have many complex electronics. So let's say complex electronic is, for example, a 420 milliampere transducer or converter that I have spoken before. So here you have no electronics, so no risk of failure due to electronics. So it's a very, very, very stable and long-term sensor. So it's really appreciated in a structure whenever you have to measure for decades. Here, the long-term stability is a parameter very important, also linked to the expertise of the manufacturing. So here, on the principle, you can see the diaphragm here, and here the seat, let's say the seat, so the main body, and here the electrocoil. So these 2 points are the clamping. So remember, the wire is clamped and put into tension. So this expertise that the clamps are made in such a way that it doesn't drift in the time is our pride. It's the main factor that makes our sensor better than the others. Then, when you get the signal, you have to convert it into engineering units, for example, Pascal or meter of water. For that, you need a calibration. So Sisgeo is proud to provide very, very dense and complete calibration report for many and almost all the sensors that we are producing in the full catalog, especially here for piezometer. Each sensor that you receive and its product produced get this process of calibration. So how does it work? We put the sensor on a bench, so connected to a pressure reference pressure sensor, And we define 6 steps from 0 to the full scale. We define 6 steps. We raise the pressure and measure the signal and go back to 0. Then we obtain a table. In this table, we compare the reference pressure given from the bench to the measured signal. We make an interpolation in linear and polynomial, and then we calculate the theoretical error from it. So the sensor is compliant. So here you can see on the bottom right part, compliant. It's compliant if the error taken from this interpolation is lower than the maximal permitted error that is stated in our datasheet. That means that when you are reading a datasheet from us, the value is the worst that we can give to the client. So the sensor is always better than that. If the sensor is not compliant, it goes to the trash. So you are certain that it's a good sensor always. Now, let's speak about something quite important for the piezometers. They are the filters. We have spoken about it, but now let's focus a bit about it. What is it and why is it here? So you remember the diaphragm is located in the piezometer body near the tip. It must measure only the pressure of water. So you don't have to measure the total pressure, so not the pressure exerted by, let's say, the load and the water, but here only the water. This means that you have to have a, let's say, a filter, a medium that allows only the water to come inside. So this is the water chamber here, and it has to contain only water and not air and not soil. So the filter basically is a disc which is made of material with controlled porosity. So this porosity has to be chosen according to the medium to monitor. So you don't choose the same filter to inside the same ground. So the chamber and the filter, so both, has to be anytime saturated with water. It's very important. So if you have air coming inside, then your readings will not be as accurate as you expect. So you need to be certain that this zone here is completely and anytime full with water. Which filter to use? So you have to choose first and then saturate the filter corresponding to the use and to the needs. You have 2 types of filter basically in Sisgeo: HAE, high air entry, and LAE, low air entry. So the HAE filter is a disc made in ceramic with a very small porosity of 1 micrometer. The advantage is that it does not desaturate with gravity. So when you take it in the hand, it stays always saturated for a long time, let's say. And the main feature is that it blocks the very fine particle of clay. The saturation of this filter is not made in any way, so you have to use a pressure. You have to use a pump. So this pump that we can provide allows to saturate this kind of filter because it's high air entry. So you need to raise the pressure above 1 megapascal in order to let the water come inside. So it's suitable for very, very fine clay material, also for salty water, so charged with the salt, and partially desaturated ground. So it's very useful, for example, when you install a sensor directly inside an embankment. So the embankment is not saturated at the time you are installing. So it's interesting to have a filter that does not desaturate by himself. So this is why we somehow use HAE filters for this kind of use. The LAE filter is the standard for us, so it can be made in stainless steel or polymer, plastic, which is called Vion. The saturation is quite easy. You just have to let it in a bucket of water for 1 day. So the difference is that sintered stainless steel is very robust, so it cannot explode or be breached by fines and particles or pebbles or rock. And the contrary, polymer is a bit more fragile, let's say a bit less robust, but it's not so sensitive to corrosion. It's not sensitive to corrosion because it's made of plastic. So this is the main difference. About the data collection, you can use handheld readouts or data loggers. So the difference is that handheld readouts are giving only one value at the time where you are measuring. For example, in Sisgeo, you can use the analog universal CRD 400, or you can register and convert the electrical readings into the engineering unit using mind readout. So mind readout is quite modern handheld readout, which can use a wide variety of signals and also convert the signals. About the data loggers, you have two main types of data loggers that can be used with piezometers, which are wired system like OmniaLog in Sisgeo, or wireless system like our new colleagues Sensive are greatly doing now, and our previous range Wirelog. Then from the data loggers, you will have the ability to push your data into a web platform, a database, and this web platform aims to display in a smart way the data in order that the stakeholders will understand the reading in the context of their building and the construction and the activity. So it's made for interpreting and alerting and take decision at the right moment. Then we have spoken a bit of piezometer sensors, but now what would be important is to see what are the different piezometer sensors that we can provide and why are they so different. So basically, the piezometer can be used in plenty of application in the geotechnique or in the construction in general. Here you can see a non-exhaustive list of project or situation where you can find those piezometer. Mainly, we can encounter these piezometers in sensors in dikes and earthfill dam, deep excavation processes for metro, for example, also in landfills and mining also as well, and phreatic level monitoring and reservoir. It is not exhaustive, and I cannot detail all the application of piezometers. It is a part of the design. You will find detailed application notes on our website, and I hope I will perform an upcoming masterclass, and inside this masterclass I will enter into the detail how to use and where to use the piezometer in this kind of project. About the sensor themselves, so we have first the standard type. So the standard type is the one that you encounter with the filter. So we have spoken a bit about, but the common characteristics of the sensors are that they are made in steel body, so stainless steel body, with a filter chip made in convention LAE or HAE. The technology embedded is in vibrating wire mode or strain gauge. Their range can go from 170 kPa to 5 MPa. And the common diameter is 27 millimeters. So it's quite thick. The body is quite thick in the cylinder, except for one model. So this one is very small here, PK20. So the PK20 is a vibrating wire sensor, very thin, that can enter into smaller piezometer tubes, for example, 20 millimeters of diameter. And just pay attention when you're using this sensor, because the body is made of steel, which is thinner than the standard one. And because it's thin, it's not suitable for being buried or to be installed very, very deep when you have some anisotropic strain. In this case, we will not monitor only the water effect, but also the earth and the loading effect. This is why this sensor has to be used only in protected environment and not too deep. About the piezometer sensors, so the standard ones, so you can use them anytime, I would say, in open systems, standpipes, Casa Grande, or in closed systems. So in this closed system, mainly they are used to monitor the pore water pressure. Then you can use the classical installations and sandpack, bentonite plug, grout, or you can directly embed and bury the piezometer inside the earth body or the material, or you can even grout directly the sensor inside the medium, the borehole or whatever you want. You can directly grout it inside. Then from this standard piezometer, we have some special versions. So the first one is the titanium version. The titanium version is used for open and closed installation because it's a standard piezometer, but it's made for aggressive environments. First, its cable is resistant to acid conditions, so pH down to pH 1, and the main body is all made in titanium steel alloy. So this titanium steel has the property to be oxidized, and when it oxidizes, this oxide of titanium is quite insensitive from oxidation. So it's oxidized first and then never again. So it can be used really for landfills, marine environment, and also tailing dams, for example. A small focus on the barometric influence. So using absolute piezometers in open mode will raise effect, an unwanted effect. You remember here the anatomy. Inside the main body, you have a sealed zone. So that means that the air here is trapped from the construction in the workshop. Here you prefer workshop in Milan. So this air is trapped from this moment and will never move. So the pressure value will never move anytime. Then when you measure you place your sensor inside, for example, standpipe, then the pressure that you're measuring contains two values. The first one is the water level, and the second one is the atmospheric pressure. So when you have good weather, the pressure raises, and then when you have bad weather, the pressure is low. So this effect will affect your readings, as you can see here on the graph. This is a pure example. Here in blue, the atmospheric pressure, and in red, this is your reading from piezometer. So it's affected by the atmospheric pressure. So it needs a correction, and therefore it needs an additional sensor. So this additional sensor is also a pressure sensor, but not made for measuring water, but measuring atmospheric pressure. So in order to have a good comparison, you have to monitor this atmospheric pressure at the same speed, at the same steps from your piezometers in order to compensate anytime the value coming from the atmospheric pressure. Even the norm, the ISO standard, requires a site calibration for every installation of absolute piezometers. For that, it's very simple. You take your sensor in the air and then you measure the zero value. So inside the air, this is your real zero value at your site, because depending on the altitude and depending on the weather, then you will have some differences from our zero that is stated inside the calibration sheet. Then I hope you understood this principle, because then we have a special version, which is the relativation version. So the relativation is mainly used in open installation, so in lake, in channels, in standpipes. For that, so we use compensating tubes. So inside the cable, inside the main body, it's not only a electric cable, but you will find a small tube which is linking the surface, so the atmosphere, and the main body. So the body inside the sensor is no more blocked and no more sealed from its pressure. So then you will compensate mainly the atmospheric pressure. You have the same atmospheric pressure in front of the diaphragm and behind the diaphragm. So this value is compensated. So it's good with this sensor because you don't need any barometric measurement on the site. And then you have also the special multipoint version. So the special multipoint version is mainly used and only used, in my opinion, for closed installation. So the aim is to measure at several levels the pore water pressure And for that, you have to use a special method. It's the fully grouted method. So this method aims to gain time and to simplify the operation, because otherwise you have to make stepwise the installation of one piezometer inside sand, and then to plug with bentonite, and then to grout, and then to plug. It's very long and complicated. Here it's quite simple. And why does it work? It works because on the principle, the pore water pressure is acting very, very locally. So mainly in a local zone in the horizontal plane of a piezometer sensor. So any vertical change are quite negligible. So the success of this installation relies only on the permeability and the quality of your grout. So the permeability of the underground, the geology, has to be known for the entire column. And if you have very, very, very important differences of permeability between two layers, then you have to use several grouts. Also to note that this method is not suitable for big settlements. So if you have more than 15% of settlement of the total length of the borehole, then you have the risk that your grout is being broken, and then you will have cracks that will drive the water outside of your interval, and then you lose all the overpressure, and then you cannot measure properly. Last but not least, some modified filter tips. So here you don't see anymore the filter tip that you have seen before. The common characteristics are always the same. So steel body with a sensing part, with a cable. Then you have the technology, vibrating wire steering gauge. The ranges are quite different. You can have greater ranges here. In the drive-in version, here the conical tip is quite large. So it's larger than the sensor body. It's made for very soft clay grounds. And the installation is quite particular because you insert this piezometer inside the ground by pushing. So you can push with a hand or with a tool or even with a machine. But you have to pay attention because driving with a machine can raise the pressure and then damage the diaphragm. So it's a bit different from a CPT testing. So the CPT testing is made to make a test at a certain moment, so to test the resistance of the soil. Here, the purpose is to monitor the pore water pressure. So it's not exactly the same. And because it's for very soft clay grounds, we use only HAE filters here. Removable version. So this sensor has a specific head with an O-ring, and it's made in order to enter inside our Casa Grande filter. So you remember the standpipe with the single column? Here we have a conical port, and inside this conical port we can lower a sensor, which is this one, removable sensor, and this sensor is applied on this conical shaped port with means of brass ballasting weights. So these weights are made only for two ranges of pressure, only for 2 bars or 5 bars. The filter is in low air entry version, and let's say it's suitable for short or medium term monitoring. So the advantage of that is that it's removable. So like the name indicates, you can retrieve it and then put it in another borehole. And the principle is that it reduces the volume of the chamber. So instead of waiting that the water raises and stabilizes here, the volume is quite small. So it reacts quickly. And the very last model that we provide is the threaded version. Let's say it's not a piezometer. It's exactly the same sensor as previous, as the before, but the head is not a filter and not connected to the underground. It's not connected to the environment. It has a thread, and this thread can be used for multiple applications. For example, here in the case of gravity dams, concrete dams, we can here monitor the uplift pressure. So the uplift pressure appears when you have a lot of water behind the dam, and here, in order to monitor this effect, we install a special piezometer standpipe, which is a closed system here because it's linked to a manometer, and then to a pressure transducer. Also, we have this system that many of you, I think, know. So this is the settlement gauges. So we can install multiple sensor like this, and this sensor is connected to a T-shaped connector, and all the sensors are linked together with water lines. And then when a sensor is raising, then its pressure is lowering, and then when the sensor has settlement, then the pressure is raising. So with the pressure, we can monitor the settlements. And on the right, you can see another type of use of these sensors with threads is connected with a pressure pad. So when you have a pressure pad like this, it's filled with oil, and this oil is then connected to this sensor. So when you have a pressure applying on this pad, then the pressure raises. It's quite stupid, the principle, but you can use for many diverse applications. And here you can see the flat jack. So the flat jack testing, if you know it, it's made in order to retrieve and to find back the strain and the stresses that are contained into a very old construction site. So you insert this flat jack, and then you raise the pressure, and then you perform a measurement in order to retrieve the initial stresses. I don't explain more because I can take 1 hour just to explain this principle. I hope you enjoyed it. So that was the explanation of all the piezometers that we can provide in Sisgeo. So now let's open, we are just on time, so let's open the session of question and answers. And I'm very afraid because there are many of them. Okay, so let's study a bit what you have written here. So what type of piezometer should be used to measure the groundwater level in limestone rock? So limestone rock is a medium. So the medium has to be evaluated in terms of permeability. So whenever the limestone is permeable, then you can use a piezometer with LAE filter, for example. Let's say limestone should not release too many fines and too many small elements. So principally, it could be used with a LAE filter, in my opinion. Also, it depends. So to use a sensor or to use a standpipe depends also on your budget and how you want to retrieve the measurement. So I don't say a sensor is to be used at any time. No, you have to choose the monitoring system according to the, let's say, the capabilities or your needs of retrieving the data. So if you use a sensor and you use a data logger, you will get plenty of data. So you should also have the means in order to retrieve and to convert and to analyze this data. So sometimes it's much better to have a standpipe and to measure. So in order to answer to your question, it depends mainly on the permeability, let's say. Let's go back to the question thread. So what is the purpose of using bentonite clay if we already filling with grout in the annular space? So the grout, when it's well made, when it's really, let's say, composed of the right elements, could make the thing. It could make the deal, and it could accomplish this mission of sealing. But we often see that there is a difficulty of injecting this grout without being affected by the water, which is often present inside the borehole. So the grout that you are pumping sometimes just at the beginning can be mixed a bit with water, and then it will lose a bit its property. So there is a risk that the grout that you are injecting is not 100% like you expect. So you have some risks in order to get the right composition. So the main, let's say, the main component that ensures that it's always stable, that always the same, non-depending from the condition inside, are the bentonite clay. The bentonite clay is made of some balls. So these are some pellets of bentonite. So you just let them fall, and when it falls, then it swells, and it's much more efficient in order to master and to be sure that your sealing is made properly. Then piezometer, once calibrated, how long can it be used? Can it be used at multiple locations, one after the other, or do we need to recalibrate them? Good question, because the answer is not simple, because the answer of things in general are never simple. Let's say a piezometer is a sensor. So piezometer sensor is a sensor. A piezometer in general is not a sensor, not always, but let's speak about piezometer sensors. So once calibrated, it should be theoretically recalibrated over time. But we cannot recover piezometers in some ways. If you install it in the deep underground and then you grout it, then it's lost forever. So you cannot retrieve it and recalibrate it. So no, it's not feasible. That's why you have to choose your supplier and your sensor according to the best performance on long term. So we can guarantee that. So this is the only answer I can give you for this kind of piezometer. But speaking only on the removable sensor, let's say, yes, theoretically, every 3, 4, 5 years, you could send to us in order to recalibrate it. So the laboratory, so the workshop has to be certified for that. So that means you should use only Sisgeo for recalibrating your sensors. So if you use a sensor, and what happens if some air is entering in the sensor filters? Will it affect the measurement or damage the sensor? The answer is you have to avoid anytime the entry of air. So it's not really the entry of air, it's the outcoming of water. So the water is coming out, and when the piezometer is drying, then you have air trapped inside, and when the water comes back, because it's a closed chamber, and when the water comes back, it does not flush the air. So there are other systems that can flush the air, but they are not piezometer sensor. It's complicated and big, massive systems, like the standpipe piezometer with the flushing. In this case, here, you have to position your sensor in some, let's say, anyhow, in order to avoid that water comes out. For example, if you fear that you have a risk that the water, environmental water, goes out, or there isn't anymore, then you can just put your sensor upside down. So that means the filter upwards. See, if the filter is upwards, then the water inside should not escape, can evaporate somehow, but should not escape. And in this way, you can mitigate and then reduce the risk that the sensor goes unsaturated. Because in this case, yes, the measurements are not so accurate anymore. You will get measurements. The sensor works, but only the quantity, the values are no more accurate in this case. Then, what is the range of permeabilities of ground where piezometer sensor in vibrating wire mode can be used? I would say any, because we have different ways to equip the filter, so filter in HAE or filter in LA. But basically, I would say, if you read carefully again the presentation, then you should not use piezometer when the particles are thinner than 1 micrometer. So I don't know if it's common. I think in clays somehow you can maybe have this effect, but and this dimension. But range of permeabilities are, I would say, all. Question, interesting. Is the accuracy of 170 kPa probe similar to the 350 probe? So in percentage, it's the same. That means that the greater range, the smaller accuracy. That means a sensor with 350 kPa range is 2 times less accurate than 175. So because the diaphragm has a different thickness. So for the small range, the diaphragm is very small. Just imagine for atmospheric pressure, the diaphragm is a kind of membrane, is a membrane like a paper sheet, like a very small plastic sheet. And for 5 megapascal or 30 megapascal, you have a big coin here that is very hard to deform. So the sensitivity, so the accuracy is less for a bigger sensor than a small sensor. Good question. In some applications, does the clay in a borehole can prevent curing the grout? So the grout, I speak a lot about the grout in my masterclass. You can find also some information inside our manual. So we have some manuals with where we recall the principle of building a grout and composing a grout. Let's say you have to choose the right cement and not to put too much bentonite inside, because the grout is made of bentonite, water, and cement. If you put too much bentonite, then your borehole will, your grout will never cure. It can happen. So the proportion has to be strictly respected. I don't know if it answers. So the clay contains inside the ground should not mix too much with the grout, because the moment of the ejection is quite a small moment. So in the geology, it's a small moment. But if you have some mud, for example, if you have mud, so not clay but mud, there is a risk. So I advise to use a protection casing. So this protection casing will avoid the mud to enter into the grout and then to change the composition. You have too many questions, people, so I cannot answer everything. I think I will answer everyone with the keyboard afterwards. I have a lot of work after that. I take a last one maybe. Can we use? Can we use vibrating wire pressure in open standpipe both? Yes, you can use vibrating wire pressure. The technology of vibrating wire or strain gauge is just the output signal. So the output signal has not any influence on the use that you will do with it. So you can use the vibrating wire pressure transducer for a standpipe, but you need to have a barometric compensation, because the vibrating wire sensor cannot be relative. Why? Because if you let enter air from outside inside the body of a vibrating wire sensor, the risk of corroding the wire is high. So the wire, you have to imagine, is a hair. So I don't have so many here, but you can imagine it's a hair. It's like a hair and made in steel, not stainless steel, and it has to vibrate. So if you corrode, if it's impacted by any humidity, then it's lost. So you cannot have it relative, but you can use it in standpipe. But you have to have, for example, a data logger. We have a great supplier called Sensei, for example, so our colleagues now. So they make a node, radio node with with a barometric sensor inside, so you can compensate the readings as well. I'm really sorry I cannot answer anybody, everybody. I was thrilled and amazed that so many people have joined the webinar. I give you some insights. So just visit the website, check the manuals, check also the FAQ, the frequently asked questions, because we have plenty of answer inside the data sheets, of course, because we have great data sheets. We have also some explanation videos and application notes. Then upcoming in a further time, piezometer masterclass. So in order to go very deeply into the installations and how does really work a sensor and in all possible cases. Thank you for having followed the presentation. I hope you enjoyed, and I say to you goodbye. Have a nice weekend. Have nice holidays if you have holidays, and see you soon. Bye bye.